Now we come to the shading algorithm for doing register allocation. Assume we have k colors or k available registers for doing register allocation in one function. K is usually or probably never 32 if we have 32 CPU registers. Some registers are reserved for other things, such as the stack pointer. Okay, anyway, we have this interference graph, an undirected graph, and we want to color it using at most k colors. What this algorithm does is not to find the optimum coloring with the smallest number of colors, but instead it tries to find a coloring with at most k colors. And it looks for nodes which have fewer than k neighbors. Okay, so why are such nodes important? Well, that node can be removed from the interference graph and the coloring can proceed. And then when the rest of the interference graph has been colored, we can put the removed node back. And there will certainly be an available color for that node. Since the node that we remove has fewer than k neighbors, if all the neighbors use different colors, there will be a color remaining for V. So we will remove it and put it on a stack, and then we continue looking for other nodes with fewer than k neighbors. Okay, so let's look at the example we had before, namely this one. So assume we want to color it with k equals 3. So this is quite trivial. As you can see, we start with this stack, and we can take A first because it has only one neighbor. So we remove it from the graph, and then we can take B, remove it. And C, it has 1, 2, 3 neighbors, so we cannot select C now, but we can select, for instance, F. Okay, so we remove it, and now all of these have 2 neighbors. So we can do them in any order. E, D, and C, for instance. Okay, so what we do now is to go through the stack and pop one element at a time and put it back in the graph and give it a color. So we pop C and give it color 1, for instance. And then we pop D and give it a color, obviously not 1, but we can say 2. Okay, E, it must get another color, so it can get 3. F, okay, it can have either 2 or 3. Let's use 2. And, well, B can get 1, and A can get 2. So, this is a very, actually, this works quite well. But there are situations when it is not possible to find a node which has fewer than k neighbors.